If you understand this one problem, you'll unlock an entire pattern. This is binary search on answer, and today we're solving Koko eating bananas, LeetCode 875. The problem looks simple, but the approach behind it is incredibly powerful. Let's break it down. Here's the problem. Koko has some piles of bananas. The guards are gone for H hours. Every hour, she picks one pile and eats K bananas from it. If the pile has fewer than K bananas, she finishes the pile but wastes the remaining time that hour. We need to find the minimum eating speed K such that she can finish all piles within H hours. Let's walk through an example. Piles are 3, 6, 7, 11, and H is 8. If we try speed K equals 4, pile 3 takes 1 hour, pile 6 takes 2 hours, pile 7 takes 2 hours, pile 11 takes 3 hours. Total is exactly 8 hours. It works. Now try K equals 3. Total comes to 10 hours, which exceeds 8. Doesn't work. So the minimum valid speed is 4. The naive approach is to try every speed from 1 upward until we find one that works. But look at the constraints. Pile values go up to 10 to the power 9. That means K could also be that large. Trying each one linearly would be way too slow. We need a smarter approach. And the key insight is, can we apply binary search on the answer itself? This is the pattern, binary search on answer. It applies when your answer lies within a known range. Here it's 1 to max pile value. You can write a function that checks whether a given speed is valid or not. And the relationship is monotonic. If speed 5 works, then speed 6 definitely works too. When these 3 conditions are met, you run binary search on the answer space instead of the array. This pattern shows up in tons of problems. Learn it once, apply it everywhere. Here's the approach. Search space is 1 to 10 to the power 9. Set left to 1, right to the max binary search. Compute mid, check how many hours mid speed takes. For each pile, its ceiling of pile divided by mid. Sum them up. If total hours exceeds H, the speed is too slow, move left to mid plus 1. Otherwise, the speed works, but we want the minimum, so set right to mid. When left equals right, that's our answer. Let's look at the code. First, the helper function. Calculate takes a speed K and returns the total hours needed. For each pile, we compute the ceiling division. If the pile divides evenly by K, it's pile over K. Otherwise, it's pile over K plus 1. We sum all of these and return. This is our checker function. Binary search will call this repeatedly with different speeds. Now the main function. Left starts at 1, right at 10 to the power 9. While left is less than right, compute mid, get the hours from calculate. If hours exceeds H, we need a faster speed. Move left to K plus 1. Otherwise, this speed works, but we want the minimum, set right to K. When the loop ends, left is the answer. Notice the template. While left less than right, right equals mid. This ensures we never skip a valid answer. Time complexity. Binary search over 10 to the power 9 gives us about 30 iterations. Each iteration calls calculate, which is O of n. It loops through all piles. So total is O of n times log of max value. With n at most 10 to the power 4 and log of 10 to the power 9 around 30, that's about 300,000 operations. Super fast, no TLE. One more time, remember this pattern. Binary search on answer works when the answer lies in a range. You can write a check function, and the range is monotonic. Same pattern applies to capacity to ship packages, split array largest sum, and many more. The template is while left less than right. If condition fails, then left equals mid plus 1, else right equals mid. Master this pattern, and you'll crack a whole category of problems. If you found this helpful, subscribe to the channel. We explain DSA patterns in a simple, visual way, binary search, sliding window, 2 pointers, and more. Hit like, share with your friends, and check out the other videos. Thanks for watching.